Hello everyone. In the previous lecture, we talked about basics of path planning or motion planning, and we also looked at one of the algorithms called the probabilistic roadmaps or PRM. In this lecture, we are going to look at a second method, which is called artificial potential fields. So what is this method? The idea is this, basically. When you want to go from the start position, let's say here, to the goal position, so what you try to do is, if you consider, for example, this case like a 2D example, so you're going to go from this point to, let's say, a point right here, then what you do is you try to create a sink around the goal position, and around the obstacles you try to create uphills, mountains, right, elevations. So you lift up the obstacles, okay, and then create an attraction sink around the goal position, so that, for example, if you have, let's say, an obstacle, a particle or water here, and let it flow on the surface, you know, the water or any particle, it's always moving toward lower potential points, right? It tries to move in the direction to lower its potential energy, right? For example, when you release a particle on a wedge on an inclined surface, it rolls down. So the same thing here. You try to create an inclined surface, really, an inclined surface which has the deepest point at the goal, but it's not just at the goal that you see a big hole, a big sink. Also, basically, in all other points of the workspace, you try to create a slope toward the goal. So it's not just one local sink, it's actually a global downhill slope toward the goal, okay? So that's effect, that thing that you create is called an attractive field. And also around the, as I said, the obstacles, you create mountains. And since a particle going on a surface does not naturally want to go up the hill and increase its potential energy, so creating these hills will basically keep away the particle from what? From the obstacles, right? And you avoid collision. So that's the whole idea. And these fields around these, the force due to these uphills around the obstacles, you call it what? A repulsive field. So you have an attractive field due to the goal and a repulsive field, or several repulsive fields due to the obstacles. And the resulting force of these two attractive and repulsive forces is what drives your particle, in this case, your optimizer location, right? Your value of, let's say, your Q's, correct? Or the position of the robot, depending on in which space you are doing the optimization. So if we want to mathematically describe it, we create a potential field, and it's artificial because we are making it. It is the sum of an attractive field and a repulsive field, where, as I said, the attractive field is going to create an attractive force toward the goal. Now, what kind of shape can we imagine so that it's just a global, not a local attraction? Well, we have some criteria here that we have to observe. First of all, the force resulting from that attractive field should go down, should be reduced in scale, in magnitude, as you get closer and closer to the goal position. So that when you are very, very close to the goal, the amount of that attractive force is almost close to zero. Why? Because if it's not, then not only it will attract you to the goal, it also makes you what? Overshoot the goal and go to the other side, and then the attractive field has to bring you back, and then you will never settle exactly at the goal position, and you just keep going around it and coming back and overshooting, and so that overshoot causes a problem. So ideally, it's like you're getting close to a red light, right? As you get closer and closer to the red light, you want to slow down further and further until you come to a full stop. That's the same thing. When you get to the goal, you have to come to the full stop, so the amount of force from the attractive field should go to zero. Okay, that's one thing. Two, as you get away from the goal position, of course, you need a larger attractive force, correct? So that it can help you travel faster toward the goal position. But when you get quite a bit away from the goal position, you don't want your force to be like insanely large. You don't want it to get unbounded. You always want a bounded force. You don't want the magnitude of the force due to that attractive field to go to infinity as your distance is what? Increasing and going to infinity. Okay? So important things, right? Now, what candidates do we have? Well, you might say, well, I might go with a linear potential field, right, for the attractive field. So basically, it is something like some gain that I can tune, and we call that gain here K attractive, and times the distance between my current location and the desired location, right? Something like that. Right? This norm here is the distance between the two locations. So of course, when you get to the point, that guy goes to zero, and as you get away from it, this value gets bigger. But the problem is that being unbounded, right? Or no? What do you think? Well, the thing is, this is the potential field. This is not the force, this is the potential field. The force due to the potential field, if you know from physics, if you have like an electric field or a magnetic field or gravity or any kind of field, the force due to that field comes from what? You are right, it comes from the gradient of that potential field, correct? So the gradient of the potential field is basically the force due to that attractive or repulsive or whatever field. So what we need to focus on is this gradient of the potential field. How does that look like? Well, you have to, gradient, you know, is like a generalized version of derivative, right? It's like when you have basically a scalar function of several variables, then the gradient is the derivative, partial derivative of that function with respect to each and every one of those variables written as a vector. We call it gradient, right? So this gradient is basically like a derivative, correct? A generalized derivative. And here, if I ask you what's the derivative of this norm function, well, the norm function also, if you look at 1D functions, the norm function acts very similar to what? To the absolute value function, correct? And if you remember, what's the derivative of the absolute value function? Yes, you're right. It's x over absolute value of x, okay? Which basically makes it 1 when x is positive and negative 1 when it is what? Negative, and it's not defined when x is 0, correct? So that's what you see here, that if I choose my attractive field to be just like a constant times the norm, then the derivative of that is going to be what? It's going to be the difference vector divided by the norm of the difference vector. So x divided by absolute value of x, where here x is the difference between current and the final position or the desired position. Okay, so that x here is the difference between these two x's in this formulation. But you clearly see that. So now clearly, as I said, this guy, what kind of problem does this one have? Remember the two criteria that we have. It has to go to 0 at the goal, and it has to stay bounded when this value of this guy is getting larger and larger. Well, clearly it has the advantage of this guy stay always bounded, right? Because when, if you look at this function, when you take the limit of that as x goes to infinity, you see the limit of that is 1 or what? Correct? Positive 1 or negative 1, because that's how this function is. In general, it doesn't really change with x value. It's, as I said, positive 1 for positive numbers and -1 for negative numbers. And for 0, it's not defined. So regardless of how much x is increasing, right? Regardless of how much x is increasing, the value of this function, really, the magnitude of it stays 1. And that could or could not be a good thing, right? So let's talk about it. First of all, the big problem it has is at 0, that we wanted it to go to 0. At 0, it's not what? Like this. It's not like that. At 0, this function has no value, okay? At this function, at 0, this function is not really defined. It's undefined at 0. Because if you remember the absolute value function, which looks like this, correct? This is the derivative of the absolute value function. When you take derivative at 0, you have no derivative, right? The function is not smooth. So at 0, this function is not defined, and so clearly this linear choice for the potential field is not going to satisfy the fact that at 0 I wanted it to go to 0. It doesn't. Okay, it doesn't. That's one thing. The other thing is, yes, when x is super big, this guy stays bounded. But when x is not really big, right? When x is not really big, still it is the constant magnitude, and that's not a good thing. What we really want, if I can plot it in 1D for you, this derivative, this del function versus x, okay, or absolute value of x, we want something that is 0 at 0, then gets larger. Now whether linear or nonlinear, that's okay. It has to get larger and larger until the x is now getting really big, then it kind of flatten out, okay, so that it doesn't grow unbounded. So we want this kind of behavior from the attractive field. And clearly, all this function can give you is the flat part of it. It doesn't give you this initial part. So how can I get this initial part, this part here? Well, I use a separate function for that. For this time, I will use a quadratic function for the attractive field. When you take derivative of a quadratic function, as you know, to get the force from it, the derivative of a quadratic is going to be a linear function, as you can see. And the good thing with the linear function is at x of 0, it is 0, and as x gets bigger and bigger, the amount of this is increasing linearly. So you will get exactly this linear type of behavior. Now, as I said, the bad thing with this linear function here for the force or the del is when x gets bigger and bigger, right, or x minus x final, when this guy in magnitude gets bigger and bigger, in this case, you'll see that del u also goes to infinity, and that's not what you want. So what can we do at the end of the day? We combine, right? We combine. We say for a portion of the attractive field, we use the quadratic function. After some distance, we use what? The basically absolute value linear function. And the boundary where you switch from one function to the other, you determine that by a distance of d from the goal position. So as long as your distance is less than d, you go quadratic. As long as it's more than d, you go linear. So your forcing function is going to be linear with distance less than d, and it goes kind of flat for the x bigger than d. So here, where the switch is happening, this is your d, okay, and it's one of the parameters that you can choose, right? It's one of the parameters that you can choose. So hopefully at this point it is clear that why we chose this multi-criteria function to achieve exactly all that we need. That's the reason. And here we need to talk about the gains that, or the parameters in this function that we have to choose. So one of them is d, the switching boundary, and there is another gain, as I told you, that you can choose to make this field stronger or weaker, and that is called k attractive. That's a gain that you can choose. Okay? So these two parameters are under your control. Now, two questions. One, is this selection for u or del u, is that the only choice you can make for potential fields? Absolutely not. It's just one of the simplest, basically. You can come up with any function that satisfies basically this kind of shape. If your function satisfies a behavior like that, okay, if it's whether it's one function or a multi-criteria, as long as you see this behavior, 0 at 0, increasing whether linearly or not until some distance d, and then kind of going bounded, okay, flatten out, or at least oscillating. Although oscillating is not really a good idea, right? Because if x is increasing, you want the force to increase, not really oscillating. So you want kind of this constant behavior, not stay within two fixed values, because that is also bounded like a sine function. But we want it to kind of go constant, not just keep oscillating. So as long as your function match this, you're good, okay? That's one. Two is, I said this is a quadratic function, well understood, but if you look at your linear function, the second part, you see it has not only a gain, it has also a constant term. And you might wonder, where do these come from? First of all, why isn't it different from that with the d is multiplied by it, correct? You clearly see there is also a d. Of course, this is not the derivative of that. These guys are the derivative of those. So if you take derivative from the bottom one, you get the bottom one here. You derivative of the top one, you get the top one here. Okay? So this is not d, this is like del. So the top one and the bottom one are not derivative of each other, but if you look at them, you might wonder why is it that we have this constant? Where is this constant coming from? Right? Because taking the derivative is clear, right? The power 2 with that 1/2 cancels, you get KAT times K attractive times the linear term, that's good. And the derivative of absolute value of x, as I said, is x over absolute value of x. This gain dKAT is here, and this is a constant. Derivative has to be 0. But again, where did this come from? That comes from the continuity conditions. And the continuity is this. Well, the function that I choose for the first part and the function that I choose for the second part, these two functions, at the switching point, which is here, they have to give me the same number. I cannot have a break in the function. I cannot have a discontinuity, a jump. They have to give me the same number at d. And the question is, how much is the value of the top one at d? So let's take a look, see how much the top one is giving me at d. So if the distance is d, the top one is going to give me how much? It's going to give me 1/2 k attractive times d squared, correct? Because that norm is equal to d. What about the bottom one? If for the bottom one I did not include this constant term, how much is this bottom term going to give me? It's d times k attractive times d. So it's going to be k attractive d squared. But this is 1/2 of that. This is full d squared kat. So I have to subtract this 1/2 from 1 to get what? Positive 1/2. So you see why this constant is added to make the value of the two functions the same. Okay? And we also need to make sure at the, if you look at the del u also, they have the same value at the switching point, do they? So if we set the magnitude of the distance from the goal or final position to d, the value of this top function is going to be d times k attractive. And is that what you get from the bottom one? Yes, because these two would cancel out, and from the bottom one you also get d times k attractive. So you see both functions, the u and del u, are continuous, and that is also extremely important. Good. So this is, as I said, one of the options I have for the attractive field. And I have two parameters to choose, the gain, k attractive, and d. Now, what about the repulsive field? So the repulsive field, it has to basically keep your optimizer or your particle away from the obstacle. So it has to kick back the object from the obstacle and say, hey, don't come close. But do we have any criterion for that one? Yes. What is it? So we want, as your distance is getting smaller and smaller to the boundary of the obstacle, we want the amount of that repulsive force to get larger and larger, and when you are almost at the boundary, the magnitude of that force is infinite. So it does not allow by any means a collision. Okay, so it has to go to infinity when you're at the boundary, you're almost colliding. But on the other hand, when you get away from the boundaries, you want that force to drop, and unlike the attractive field, the effect of which was global, correct? These functions are going to affect what? Global, all of the workspace or the search space, correct? They cover everything there. This field is a global field. You want the repulsive field to only be local. You only want each obstacle to only affect an area around them, and outside that, you don't want them to affect anything. You don't want them to impede or disturb the motion of the optimizer toward the goal position, okay? So they have to stay local. Their field has, or the gradient has to stay local and grow very fast so that at the boundary goes to what? Infinity. Now, the function clearly that you can imagine should be proportional to 1 over distance to the boundary. So here, this function rho that you see, rho of x, is the distance, and it is the shortest distance from your current location to the boundary of the obstacle. So let me show you that. So basically it means, if I go back to that first video, right? So let's say you are here, correct? You are at point P2, and the next obstacle on your way is this triangle, right? So what would you do? So if you have your LiDAR or radar or whatever device that you can measure the distance, you basically try to scan all of the points on the boundary of the obstacle, and then you try to find among these the shortest distance, correct? So let's say the shortest distance that you found is this distance here. Okay, so this point, we call it point X, which is your current location. The shortest distance that you find from this point to the boundary of the obstacle, you call it rho of X. And the point on the surface of the obstacle that is the closest to your current location, here in those notations I'll show you, you call it point B. Okay, so hopefully it's clear what I meant by rho of X, and as I show you by B. Good, so that's fine. Okay, so let's go back. So the meaning of rho is clear, shortest distance from your location to the boundary of the obstacle, and B is the point on the boundary that is closest to you. Now, why did I choose my potential function to be 1 over rho? It's clear now, because when rho is going to 0, this function is infinite, or the forcing function is infinite. We needed that. After rho becomes bigger than some value, rho naught, you drop the potential field or the force of it to 0 because you wanted it to be local. So this rho naught is a parameter that you can choose, as well as this k repulsive, which determines the strength of the repulsive force. Rho naught determines what we call the region of influence. So basically, for example, if this is your obstacle, this rectangle, then you can basically create another rectangle with an offset of rho naught in all direction around it, something like this, correct? Where this distance here is rho naught. So inside this region that I called region of influence of the obstacle, you have the repulsive field. Outside it, there is nothing. Okay, so you completely make it local. So the definition of rho naught is also clear, determines the region of influence. So K repulsive is clear, that's the magnitude, this is the region of influence. The 1 over rho is clear. Now, why would you square it? The square is to make sure that your function, the potential fields, always stay positive. And why did you subtract 1 over rho from 1 over rho naught? That's clear because you want the top function and the bottom function to give you the same number at the switching point, right? If you didn't include this term here, then the top function will not give you 0. But when you subtract from 1 over rho naught, then when your rho is equal to rho naught, this whole thing goes to 0. So the function is continuous at the switching point. So the choice is completely obvious. And now, of course, the gradient of 0 is 0, so no worries. Now, why the gradient of this function is this term here on the right side. And where do you get that one from? So if you look at this function, it's kind of like taking the derivative of some function like rho of x, but 1 over rho of x to the power 2. So this kind of like taking derivative of this. Of course, here it's not just 1 over rho, it's 1 over rho minus 1 over rho naught squared. But when you take derivative of this, correct, what would you get from calculus? So we will get negative 2 times the derivative of rho with respect to x divided by rho of x to the power 3. And that's exactly what you see here. This is power 1, this is power 2, so you have power 3. This 2 and this 1/2 are cancelled, so you have just a negative k repulsive. And here, instead of this d rho over dx, you have gradient of rho, which is the same thing but multi-dimensional because your x here is several variables. And this gradient of rho is defined as x minus b over magnitude of x minus b. So what is this one? Well, let me show you. So when you are inside the region of influence, rho is less than rho naught, what's happening in terms of the signs? This term is clearly negative. Rho is less than rho naught, so 1 over rho is clearly bigger than 1 over rho naught. So when you subtract, this has to be also negative. The rho x squared is positive, so far everything is positive. So the direction of del u repulsive is the same as what? Del rho. These are the same direction. Now, which direction is del rho? Let's go and look at this and see what's the meaning of this term. So here, if I go back and show you, if you remember, I told you this shortest distance is called rho, and that's b and that's x. Now, what is x minus b? So it means if this is the unit vector of x and this is the unit vector of b, when you subtract x minus b, it means connect the end of negative to the end of positive vector. So connect the end of b to the end of x, which is this vector here. Okay, that vector, but we are dividing it by its magnitude. So it is basically a unit vector, correct? If we call it the unit vector u, that's this unit vector. And which direction is it? Clearly, you see it's away from the boundary. And that's exactly what you want. You want the force to be away from the boundary. You want it to repel the particle, and that's exactly this one doing. So I hope the mathematical part of the choice of these functions are completely clear. They all come from the properties that we expected from a repulsive field and an attractive field. So now, how do we make this optimizer particle or a robot to go from the start point toward what? Toward the goal point, right? How do we make that happen? Well, we move in the direction of the gradient. And since your potential field is made of these two parts, when you say the gradient of the potential field here, right, that's the same as the gradient. When you say the gradient, clearly it's going to be what? It's going to be gradient attractive plus the gradient repulsive, correct? So this guy here is this. Okay? Now, why should we move in the direction of negative gradient, as you see? It's something that is well established in calculus. We call it the steepest descent. And what is that? Well, you can show that if you have a function in general, a multidimensional function like the surface, at any point that you are, if you move in the direction of negative gradients, you can also move in other directions as you want, right? But in which direction does it allow you to move down faster? The fastest, basically. It is well proven in calculus that the direction that allow you or make you move down the hill the fastest is negative of gradient at that location. And if you move in the positive gradient, that's the direction of steepest ascent. So that's the fastest uphill direction, correct? So what we do in order to accelerate this and go to the goal point as fast as possible, we move in each point in the steepest descent direction, which is based on calculus, the negative gradient. But we don't keep moving forever in one direction. As we move from one point to the next, right? Because you do this through a bunch of points, right? You don't go it in one step. You go in steps, right? You go from point 1, let's say, to point 2, to point 3, to point 4, 5, 6, right? So you keep basically updating these. Because when you move from one point to the next, the value of all of these would change, the value of the gradient would change. And to control how much you would move at each point in its gradient direction until you get to the next point, we have another control parameter, alpha, which is called the step size. Typically, it's not really a big number. We typically choose a small number to make sure that you don't basically take a large step, because if you take a larger step, there is always a good chance that you get either very close to the boundary of an obstacle before the repulsive force kicks in and push you back. So what you will see is a bunch of what we call overshoots, okay? Although it might in general make it faster, but you're going to have a bunch of overshoots, which is not always desirable. If you move very small, then you have a better chance of not overshooting, but it takes you more time to converge, okay? It's just like walking in a dark room. So when you're walking in a dark room, you don't want to go very fast because you have a good chance of bumping into something. But if you just go very, very, very slow, it takes you forever to get to what you want. So it has to be a compromise, okay, between overshoot and the convergence speed. But we typically choose this alpha to be a number that is less than 1, and typically like 0.1, 0.01 or something. It depends on how complicated the environment is. The more obstacles you have, the more weird shape they have, non-convex shape and so on, right? And the further away is your goal from the initial location, you probably need to be a little bit, at least in the first round of the algorithm, be more conservative. So you keep repeating and you keep going downhill so that you get to the point that is the deepest, right? That's your sink point, basically, your goal point. And when you get there, then you stop. Now, what do we mean when you get there? Does it mean you exactly land there 100%? No. It's never gonna happen unless you wait forever that you exactly land at the goal, at the final position. So once your distance from the goal position is less than some threshold, and that's another thing that you choose, you stop, correct? It's like your distance is initially 1, then it drops to 1/2, then it drops to 1/4, then it drops to 1/8, and let's say each time it goes down by a factor of 2. Well, how much time does it take you to go to 0? You know, it's infinite. You need infinite many terms of this geometric progression to go to 0. So you cannot practically make it 0, but once it's less than, let's say, 10 to the negative 3, 4, 5, depending on your accuracy needed in the application, then you say, yes, I have converged, and then you stop your algorithm, okay? So you see you have 6 parameters to choose. Alpha and threshold, these are just for convergence of the algorithm. For the strength of the attractive field, you do K attractive. To make the switching point, you have D. For repulsive, you have K repulsive for the strength, and then to make it local, you choose what? Rho naught. So you have 6 parameters to choose. Now, a few points important about this selection of these gains, K attractive, K repulsive specifically, and rho's. And then I'll show you a demo of it. We'll talk about the major issue in this algorithm, and we discuss some other things. So, 1. If there is more than one goal, okay, if there are more than one goal or one goal positions in general, right? So let's say it's not just, in this case, this is where you are and this is where you want to be, and your goal is not just one position, you also have another goal here and maybe another goal here. And if you call them G1, G2, and G3, and let's say I want to go in order, first visit G1, then visit G2, then visit G3. And then how do I make sure I first visit G1? Well, I choose the K attractive gain for that to be larger. That way, the field of the G1 is more powerful than the other two, and it would attract more, okay? So more than one goal, in order of priority, choose what? The K attractives from largest to smallest. That's 1. 2. If there is an obstacle or there are obstacles close to the goal position, sometimes your goal position is surrounded, or at least close to it, we have some obstacles. So if there is an obstacle, let's say right here, some obstacle like that. There is an obstacle like that right next to the goal. And let me actually make it even bigger. If I have an obstacle like that around the goal position, that distance rho that we choose to make the region of influence of this local, we choose it such that the goal never falls within that region of influence, okay? Because, for example, if here I go very large, there is a good chance that I have overlap with the goal position. And that's not a good thing, because that does not allow my particle to ever reach that. So make sure your goal is never within the region of influence of any obstacle. Choose the rows for those obstacles smaller. Okay, choose the row for those obstacles closer to the goal smaller. And the other thing that you want is if you have several obstacles close to each other. Sometimes you have obstacles close to each other. Like, for example, you have one over there and you have one over here. Correct? Again, if they are close to each other, make sure you choose the rows such that the regions of influence do not overlap. So if you choose this one, for example, large enough that here you have an overlap region, that's not a good thing. Because there are two different directions of repulsive forces, and the particles will be, for the optimizer, will be basically distracted. Plus, since you have two repulsive forces, almost there is no chance for your optimizer to go from here to here. Okay? You create kind of like an impasse for it to pass. Okay? Or if they are very big, still not overlapping, right? So still, you might not make them completely overlapping, but you make those regions of influence large enough that now what they create is what we call technically a narrow passage. So you make something like this, and then you make something like that. Then here you have a narrow passage, and it is going to take some good time and a lot of bouncing, if ever, for this guy to go from here to here. So try to avoid narrow passages, try to avoid overlapping regions of influence, and definitely do not cover the goal position with regions of influence for these obstacles. Okay, so it's needs some practice and experience to choose everything right. Good. Now let's talk about the effect of the step size, and then I come back about this last point. So the effect of the step size, as I said, small step size means you are being very conservative and careful, so you probably won't bounce back and forth too much, but it takes you more time to converge. So here you see the example. I'm trying to move from this point to this point, from red point to the green point, and I have 4 obstacles on the way. Well, the direction of the attractive force is definitely here along the line that is connecting me right to the goal. But when I try to follow that, if you can see, when I try to follow it, here I go and bounce into the region of influence for this guy. And what happens then? I get the repulsive fields which wants to kick me back. So I go like this, and then what? Again, when I come here, I try to directly connect myself to the goal. So I try to go in that direction, but again, I go into the region of influence, it kicked me back. So I keep being kicked back a few times until I get outside that region here. And now what? Again, I try to go straight until I hit the next region of influence. And then I keep what? Going back and forth again here. I try to go there, I get hit, I go back and forth, and finally what? I go like that. So instead of this straight line, I get this kind of zigzag path, but ultimately I will get there, right? Now, you see the amount of back and forth, the overshoots are not huge here. But if you see, it took about 300 iterations for this algorithm with an alpha of 0.1 to converge, right? Now here, I bumped up my alpha to 0.5, made it bigger. Clearly, my algorithm converged in about 60, 70 iterations, a lot faster. But if you look at my overshoots side by side, you see that the overshoots here are quite larger in magnitude compared to this one, right? Let me just clean this one up. If you see, the path is here kind of straight, which means small overshoots. But if you look at here, it has a bunch of more bumps, right? And here, another bunch of more bumps and a little bit bump here. So you see, the path is way smoother here compared to here. You have much less overshoot, but it takes you more time to converge. So it depends on the problem, right? It depends on the problem, because if you have more obstacles here, now you might say, what's wrong? Well, it doesn't matter. This one converges faster. Let's use this one. You're right. But here, if I had some other obstacle here, or some other obstacle here or here, then I have the narrow passage problem. And if I get entangled in the narrow passage with a lot of overshoot, going from this one to this one, back and forth, it might actually take me more than this one to converge. Okay, so if you don't have narrow passages, yes, you probably can go with larger alphas. But if you have some narrow passages between the particles, you better be conservative and be careful and very gently and smoothly pass through these narrow passages. Okay, so it all depends on the complexity, which alpha you can try, but it's always some trial and error, some tuning involved here. Okay, there is not exactly any perfect formula I can give you so that for any situation it works and say, hey, choose alpha to be like that. No, it's really a tuning, and it's mostly done by trial and error. Okay, now one last thing before I show you the demo is the major issue, as you clearly see, is being trapped in a local minima. And that's not a good thing. What is that? Well, let me show you something here. So when I'm going from here to here, Because at, let's say, a point like there, I have repulsive forces and I have attractive forces. The resultant of those will create some small holes locally, as you can see. I have a bunch of what? Small local holes, right? It's just like the surface of the earth, right? When the mountains are coming up, then next to the mountains you have also some deep areas, you have some faults and so many other irregularities, wrinkles, and so on. So the problem is, as you move on and get to the middle of or close to one of these what? Small holes, what happens? When if you look at it from the side view, it looks kind of like this, and you are here. And if I now look at the direction of the descent, there is no descent. All I can do from here is to go uphill, but the negative gradient should go downhill. So what's going to happen when I'm down there? It's what we call a stable extremum, right? If you are on the top of a hill, this is what we call an unstable extremum, correct? If you let a particle on this and just give it a small kick, what happens? It goes down the hill and keeps going. While here, if I just give it a small kick, it comes up here, but again, it wants to go what? So it moves up here, right? But what's happened? What's going to happen? Downhill is again downward, so it's going to go back to the minimum, right? If I'm at here and calculate my gradient, it says, hey, go down this direction, so I go back to where I was. And this is called being trapped. You get trapped there, and you want to leave there and go to the global minimum, which is there at the goal position. So these local minima are problematic. Now, how can I handle them? Well, one of the ways that you can handle this is by some random motion. What does that mean? As you can see here, it means if you look at the value of your x, the local position, and you see after a few iterations, the x does not change, okay? So here you're monitoring your x versus iteration number. So let's say this I is iteration number, or II, and this is x of II. Now here I just show a 1D case of it. So you see it is just moving from one point to another, going, and then here it's kind of flattened out. It's not moving anymore. If you see that, it means, and you are not, but if you at the same time you also monitor your what? Your x minus x final, and this is iteration, so this is your error term. You see it is going down, but now your error is what? Constant, right? So you can look at your error if you want. What does that mean? It means you should go to 0 to get to the final position, but you are not. So here you are trapped. If you're trapped, what would you do? Then you try to add some random motion to this. So instead of making this gradient to be simply gradient of the attractive plus gradient of the repulsive, you also add plus some random term. Okay, and that random term tries to break moving in the downhill direction all the time. So if you're here or if you're here, I'm not going to go perfectly in the downward direction. That random motion can give me what? A direction upward, and if that one is large enough to dominate this gradient, it might what? It might be able to kick me out of the small hole. Okay, so this random walk is randomized potential planner is something that many algorithms would use when they are trapped in local minima. It's not just for artificial potential fields, and they try to basically kick themselves out of those local minima using some random fields. But again, it's an optimization problem, multi-dimensional, and the surfaces are quite complicated. So you have to work with the parameters and make sure that you tune them well in this work, in this experience. But here, let me show you an example. So let's run this. Here is the same picture, the code for the same picture I showed you. alpha is 0.5. I go from an initial to the final position. This is my search area. And here we go. You can see here it is trying to go from the start to the end. I get some kicks. You can probably see the kicks here better. Right, let me get this out of the way. So if you look at the line connecting the centers of the circles, you can see the overshoots. You see that big overshoot? Because alpha was big. And here are small overshoots, and you see clearly I'm getting there and my error is dropping to 0. Okay, so this is with alpha of 0.5. There we go, I have converged. And here my threshold for the error is 1. Okay, so it's a big number, but my search area is 100 by 100. Okay, so it's a big search area. But now if I make it 0.1, right, let's get even closer. And by the way, I have one more parameter that I mentioned in the other algorithm too, a maximum iteration. You always need to have this. In case your algorithm diverges instead of converging, you make sure you break the loop, correct? So this while loop works as long as your error is bigger than threshold, means you have not converged, and your iteration number is less than max iteration allowed. So always make sure you have some mechanism to break the loop in case it is not converging. So here again, I go with the same thing. I make my threshold tighter. So let's see whether it converges, and if it does, how much more time it takes for it to converge. So the behavior should be the same all during the motion, except for the end of it, where you determine whether it's converged or not. Okay, so the threshold is not going to change the overall behavior, just the end behavior. So you see so far it's kind of exactly like the previous case, and should not show much of a difference. Now here it takes a little bit more time. You see there are more circles here, but I guess I converged. But now if I can zoom into here, you see this small extra steps that last time I did not have to take to bring my error down to 0. Let's see if it's converged. It's converged, yes. And now it takes a few more iterations. So can I make it smaller? Probably yes, because this is not really a complicated case. It just, again, takes more iterations, but it should definitely do the job. Okay. Okay. So let's focus on this one. There we go, you see? But I guess now it has converged. See, now you have more. Instead of 60, now it's going to 70 iterations. But it's not a big thing because it's already there. And you see here, I have more circles, but I could get there ultimately. Let's see if I can focus here and show you. You see? Now I'm almost perfectly at it. And this is how it works with this. Now if I change my step size to a smaller number, definitely takes more time, but behavior is smoother. And here I have two sub-functions, sub-utility functions that will give me the attractive and the repulsive forces. Okay, so let me show you. So here I have a del u function and a del u attractive and a del u repulsive. Okay, And then in the negative gradient of that with magnitude alpha, I move. So as I said, I have two utility functions, if this one allow me to open it. Here, see this still attractive. Of course, it has to wait until this graph is over, then it does open it for me. But here, that's my path, you see. Without too much of collision and back and forth, it is going very nicely, very smooth. But you clearly see I need a lot more iterations for it to happen. And here I have created these obstacles basically by defining their corners. And then basically I have also a utility function called obstacle generator that I pass to it the size of the area, the position of the corners, and then it generates for me a binary picture that has zeros and ones. Zeros are the obstacles, one wherever it is free to navigate. Okay, and then I do some animation and so on and so forth. You see, you still have to wait. And clearly it is going to go to several hundred iterations, but the behavior is very, very smooth, as you can see. So a small alpha is good for narrow passages and shapes with tons of obstacles that are typically close to each other. Otherwise, you can bump up the alpha. If you see you are not getting stranded back and forth and not big overshoots, then you might try to, as I said, boost up your alpha, make it bigger. There we go, we're getting there. Already at 300 iterations instead of 70 of last time. And I'm getting there. I see the small curve at the end again because I want it to be very close to the goal. And I guess now finally I have reached almost. Seems like still moving. Yes, still moving. Because now you're even moving smaller and smaller, it takes a lot more time for it to go to that small threshold. You see, it just keeps moving. And let's see if it even converges that small threshold. There we go. Now it did, so it stopped. And you see, it just went from 300 to 350 to make that threshold that was 1 to make it now less than 0.01. So you have these many extra steps just for bringing down the threshold. And as I told you, I have an attractive field that is generating that. I have a repulsive field that generates those two functions, the multi-criteria function, and I have an obstacle generator that will basically creates a binary image for me, right? So I'm using the command poly to mask, and I pass the coordinates of the polygons for the obstacles to it, and it creates a binary mask for me, a BW, binary mask, and then I will pass all of that to this function to move in the negative gradient direction and check the error in each iteration and check how many iterations I have passed. And then it does the animation and so on. Okay, so hopefully this video was useful to you, and I will see you in the future lectures with videos about two other methods of path planning, A star and tangent buck. I go briefly on them because they are quite complicated methods, and I don't go into deep math of them, but I explain them enough for you so you understand them. And finally, we go to trajectory generation. Thank you so much. See you in the next video.